Okay, so this is our new unit. And I just need to get this all. So I'm just getting my board plugged in, drawing board. Okay, so the learning goal here is to investigate the inverse of an exponential function, exploring the logarithmic function. And so it says, recall the inverse function is the reverse of the exponential function. That's what we're filling in there. And really, we're just switching the x and the y and solve for the new y. Okay, so to find the inverse of a function algebraically, switch x, y variables, then solve for y. So I'm going to switch. This is just our very simple example here. We switch the x and the y, and then we isolate for where y is. So we're going to have to get rid of this squared by square rooting. Right? And whenever we take the square root, that undoes that squared. When we take the square root ourselves, we have to remember to take the positive and negative answer for that. So y plus 3 is opened up now, and we've got plus or minus the square root of x on the left-hand side. Now I'm getting rid of this plus 3 by subtracting 3 from both sides. And that can go in the front of this plus or minus x or off to the right of it. So I'm going to write it over here, just making sure that we know that this square root is just taking the square root of the x, not the minus 3. Okay, so we can't then replace this y with f to the negative 1x. We can't use that. And that's because it fails the VLT. So if we think about what this started out as, it started out as a parabola because it was squared, shifted to the left 3, but it was a parabola. And then when we do the inverse, it turns out to be a sideways parabola, right on its side, something like that. And it fails VLT. So we can't use that f to the negative 1 of x notation. Next, it says to find the inverse of a function graphically, reflect the function in the line of y equals x, or just switch the coordinates. Yeah, it's like the simplest for the points of the original function. So if we had the original function being x and then y is equal to x squared, we'd say negative 2 is my input. When it goes to be squared, right, we go like that. I don't know. We know this already. Negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. Okay, so those are my original points for a parabola. Here we go. There is my original. That's my original. And then we can, I'll switch colors and go with black here. So for my inverse, I'm just switching the position of each ordered pair. I'm switching the x, y. So now I'd be at 4, negative 2, 1, negative 1, 0, 0, 1, 1, 4, 2. When I go to graph those, I get negative 1, negative 1, 0, 0, 1, 1, 4, 2. We get that sideways parabola. Okay, so this is my inverse function. And it's a reflection through the line y equals x. I'll put that in. All right. We knew all of that, but it's nice to review. Next question, this is where it gets specific to the new stuff. What does the graph of the inverse of an exponential function, and this is the simplest one we have, y is equal to 2x look like? So we're going to create the table of values for this exponential function here. So when we choose the value of -3, we input that into the equation. And then we remember our rules for exponents. So whenever we've got a negative in the exponent position, we're flipping the base. And that's all to the 3. So it's 1/8. And then I'm going to put that as a decimal because it's easier to graph. Right, so -3 and just a little bit higher than, can't even tell, right, than that x-axis. 2 -2 is going to be 1/4 or 0.25. So again, 2 to the left and just a little bit above the x-axis. 2 to the -1 is 1/2. Okay, so now I can be like a little bit higher now. 2 to the 0, whenever we've got the exponent of 0, it outputs 1. So 0, 1, special point there. Next is 2 to the 1, so that's 2. So 1, 2 is here. 2, 2 is 4. So 2, 4 is up here, and we're exponentially spiking now. Okay, so last, we've got 3 to the 8, and that's going to continue rising quickly. So I'm going to connect my points here and recognize that there's a horizontal asymptote. All right, so there is my curve, my exponential curve. It's never going to cross this x-axis. So we say that that is our horizontal asymptote of y is equal to 0. And what does the inverse look like? So that was the original. Now I'm going to go and turn to my black pen here, and we'll do our inverse here. So all we're doing is swapping our x and y for each of the ordered pairs that I created. So here's my new table for the inverse function. It's going to be, I'll just use the decimals here. And I'm going to plot them. So it's really close. It's an x value moving to the right, 0.125. So it's very close to that y-axis. It's very close, but it's dropping down to -3. So I'm going to drop down here somewhere.
Miss, I think that lesson is 3, 8, 3.
Ah, thank you.
Yeah.
Thank you, thank you. You're correct. Okay, and then I'm going to go 1/4 to the right and then 2 down. 1/2 to the right and 1 down. 1 to the right and 0. 2 to the right and 1. And 4 to the right and 2. And 8 to the right and 3. Okay, so I'm going to put in my curve here so I can see that there's been a change of my asymptote here. Okay, so this is now my vertical asymptote. is going to happen at x is equal to 0. Okay, guys, so this was my inverse function, and the blue one was my original. So there's going to be just kind of similar to my reciprocal function unit, right? There's going to be some changes of their key points and changes of where those horizontal asymptotes are. And that's going to follow a pattern that we'll memorize to generate graphs and to understand these functions better and their inverses better. So next, what is the domain and range of the exponential function? Okay, so this is like the original in blue. I'm just going to put these answers all in green. Okay, so my domain of the original is XER, or X is an element of the real number set, and the range is YER such that Y's are greater than 0. Okay, so let's double check that. If I look to the blue, yeah, XER, and then we're always going to be above the y-axis, so y's have to be greater than 0. Does the exponential function have a vertical or a horizontal asymptote? We put that in. That's a horizontal asymptote at y equals 0. The graph of the inverse, okay, we did this already, check. Is the inverse of an exponential function a function? And if we look at our example, yes, it is, because it passes the VLT. What is the domain and range of the inverse of the exponential function? So the domain is x is an element of the real number set such that x's are greater than 0. And the range is y is an element of the real number set. Okay, so just looking back and double checking that. Yeah, the domain has to be bigger than the vertical asymptote here, and y's are all fully available to it. Okay, and so that's like a switch of the domain and range of the original, right? Those two switched, and the horizontal and the vertical asymptote switched. Does the inverse function have any vertical or horizontal asymptote? So this means that if there's a vertical asymptote at x equals 0. So that pattern of switching the range and domain and the asymptote is our pattern for the relationship between the exponential function and its inverse. Okay, so now we are going to go back to the blue pen, and we're going to graph the original function and its inverse on the same axis. And so I'll go through this, but just keep in mind that this, I think this was supposed to be done as an investigation, but I'll just like kind of slowly go through it. We will investigate together. Okay, so the graph of the exponential function, when the x's are chosen for us, so if I sub in this -3, right, the negative means that we flip it, and then we evaluate the exponent. So that's really, yeah, that's really 2 to the 3. I wrote that down wrong on my page. Okay, my next one is going to be 1/2 to the -2. So then that flips. So it's really 2 to the 2. I won't write out all these steps now, or 4. Okay, so this is 1/2 to the -1. So that's just 2 to the 1, or 2. 1/2 to the 0 is 1. Anything to the power of 0 is 1. And I'm going to write these ones as decimals, so we're going to be graphing them. Okay, so now I'm going to graph these. 3 to the left, 8 up. 2 to the left, 4 up. 1 to the left, 2 up. 0 to the left, right, 1 up. 1 to the right, half up. 2 to the right, no, one to the right and a half up. That didn't take. 2 to the right and a quarter up. And 3 to the right and an eighth up. Okay, so there is my original. Oh my gosh, I'm missing all my dots here. You guys do a better job on paper. Here's my original function, and that is a decay function. Okay, so the first example that we looked at was a growth, and this is a decay, exponential decay, and that is because our b value, the base of our power here, was between 0 and 1. So this one was the base is less than 1 and greater than 0, so it is decreasing. Okay, and now we're going to graph that inverse as well. Yeah, because it says to graph its inverse as well. So I'll switch over to the black pen. I'm not going to rewrite the whole table of values again. I'm just going to switch them. So it's 8 to the right and 3 down. It's 4 to the right and 2 down. It's 2 to the right and 1 down. It's 0 to the right, left, and oops, 0 to the right, left, and 1 up. So I'm right here. And then it's, wait, did I mess that up? 8 to the right and 3 down, 4 to the right and 2 down, 2 to the right and 1 down, 1 to the right and 0 down. Yeah, I messed that one up. And then I'm at a half to the right and 1 up. I kind of need to get rid of that little one. Just like so. Okay, so that one was 1 to the right and 0 up, down, and then it's a half to the right and 1 up. So it should have been here. And then a quarter to the right and 2 up. So it's right here. And then an eighth to the right and 3 up. Okay, so we can see where it's approaching. It's approaching the the y-axis. Oh my gosh. This is not easy with this board. Drawing this in. Come on, come on, come on, come on, come on, come on. Okay, I missed some of those there. Okay, so this is my inverse function. And we can see that it's still decreasing. And what we'll do is also write in that this is now, for this inverse, we've got a vertical asymptote at x is equal to 0. But for my original, I had a horizontal asymptote at y is equal to 0. Okay, so those two have switched again. So is the inverse of this exponential function a function? Yes, it still passes the VLT. What is the domain and range of the inverse of the exponential function? So the domain is x is an element of the real number set, such that x's are, and this is for the black here, x's, what is the domain range of the inverse of the exponential function? X's are greater than 0, right? Because we can't go past that y-axis. And the range is all the values are available to it, so it's an element of the real number set. And does the inverse function have any vertical or horizontal asymptotes? Yes, it has a vertical asymptote at x is equal to 0. Okay. And just for thoroughness, I'm just going to put in my y is equal to x, that reflection line, into both of these. Okay, so that's y is equal to x. And down here, okay. So here's our summary box. So we'll fill that in blue in summary. The inverse of the exponential function of y is equal to a to x is the logarithmic function that can be written as x is equal to a to the y. So this is about the inverse here. So this is with the x and y already switched. Now this can be rewritten as, in terms of a logarithm, as y is equal to log a x. So these two here are the same function here, and it's based off of the original switching of the xy of the original function. But when I show it as this equation up here with just the xy switch, this can be rewritten as a logarithm. Okay, so this is the logarithmic form. I think I missed something up here that I don't like how I wrote that. I'm going to write logarithmic function. I think that makes a bit more sense. And is read as the logarithm of x to the base of a. The logarithm of x to the base a. Okay, so as with the exponential function, when a is greater than 0, this is always, well, these little bullets are when we've got that growth situation happening, when a is greater than 0 and a cannot equal 1. So if a is less than 0, then you raise it to the rational power. You may not get a real number. So for example, if a is equal to -1, then when we take -1 to the half, that means that we're going to be doing the square root, right? Because when we've got that half up in the exponent position, we're taking the squared root, right? There's a little index 2 in that little pocket there of -2, which isn't real. Okay, so sometimes there's errors there. If a is equal to 1, then no matter what x is, the value of f of x is equal to 1. And when we have 1 to the x, it doesn't matter what that exponent is, you're still going to output an x, which is not an exponential function. That's why you can't have that a value being a 1, and that's why a has to be greater than 0, right? So since x is equal to a to the y and y is equal to the logarithm of x are equivalent, a logarithm is an exponent. Log AX means the exponent that must be applied to the base A to get the value of X. The exponent, so that's the most important thing here, that's bolded. So we'll give that a highlight. The exponent that must be applied to base A to get the value of X. And so today's big idea of today is just getting that in our minds. So if we have the logarithm of 8 here, this is really meaning the exponent that must be applied to this little subscript number 2. What does 2 need to be raised to equal 8? And so I'm just going to write that down here. 2 to the blank, 2 to the x, equals 8. Okay, and so that, it's 2 to the 3. So that's why we say that this logarithm of 8 is equal to 3. The exponent that must be applied to the base of 2 to get 8 is 3. The shape, and so even another thing to think about is that this little subscript number, 2, it's like kind of hanging off the bottom of that logarithm. So that bottom number becomes the base. So the base of 2 to what exponent becomes that argument 8. Okay. So the shape of the graph of the logarithm function depends on the value of the base. When a is greater than 1, the exponential function is an increasing function. Okay, so that's like growth. When the logarithm function is an increasing function, because we can rewrite these exponential functions as logarithms. Okay, hold on for one moment, everybody. Okay, sorry about that pause, guys. So this little highlight here is the most important thing. It's like the key to understanding how to flip between the logarithm and the exponential format. Okay, so that little subscript number that's hanging off the bottom of that G is like the base of the exponent. And the 8 is kind of in the argument position. So that's like always the answer. And we'll be thinking about what that exponent needs to be to make that base equivalent to that argument. Okay, so where were we? So when the base is between 0 and 1, that's when we are doing the decay situation. So that's when we're decreasing. And that logarithm function is also going to decrease. So the domain of the exponential function is XER, and the range has a vertical asymptote for YER functions. And then when it comes to the exponential, just double checking, maybe this does not make sense, sorry. I just filled that in for the wrong line. I was looking at the wrong spot because that doesn't make sense. This is supposed to be the the x-axis is the horizontal asymptote for the exponential function. I'm just throwing down words here. I'm looking at the wrong spot. Okay, so the proper fill-ins here are that the x-axis is the horizontal asymptote for the original exponential function. The y-axis is the vertical asymptote for the logarithmic function, because really what we're talking about is that the inverse of the exponential, that new curve, and I keep spelling this wrong, is that inverse curve. The logarithmic is the inverse of the exponential. That's what we're just kind of changing the vocabulary there. The exponential is the original, and the logarithmic is the inverse. Okay. The y-intercept of the exponential function is 1. The x-intercept of the logarithmic function is 1, because those two switch. Okay. The domain of the exponential, the original, is XER. The range of the logarithmic is YER. Okay, and then the range of the exponential, where we've got y is, oh gosh, YER such that y's are greater than 0, that's going to flip for to the domain of the inverse, or the logarithmic one. Okay, so we saw that with our investigations. And now this is just putting it into the summary box. Okay, but it's just what we were looking at from the previous two examples, that the horizontal asymptote becomes the vertical asymptote of the logarithmic or the inverse, and that the domain and the range switch between the original exponential format to this inverse, the logarithmic format. Okay, so now we're going to be looking at just the equations and switching them from their original form to their inverse form, or from the exponential form to the logarithmic form. So this is state the inverse functions for the following exponential functions in exponential form and in logarithmic form. So I'm just going to wipe out the function notation to start, where we'll place that with the y. And in terms of its inverse function, I can just switch the x and y, just like we always did back in Unit 1 and back in grade 11, to get that exponential format of the inverse. Okay, so this is really f to the negative 1 of x. Now, that's what we're talking about here. And so we write x equals 5 to the y. And that's in the exponential format for the inverse. Now that exponential format can be put into logarithmic format, which is what we want to do as well. So this is the exponential format. Now for the logarithmic format. Okay, so here's where we're gonna learn something new. We knew the x and y switched, but now we've got to put in this log kind of word. And so here's kind of how we're going to think about it. That answer part that is here, that is already by itself, this is like the answer, is going to be the argument. So I'm going to write log of that big X. The little subscript that comes next to the logarithm, that's like hanging off the bottom of the G. That's going to be the base that the exponent originally had. So we're going to put a 5 as the little subscript. And y, the exponent, is going to be by itself on the outside. So this is the logarithmic format. This one was the exponential. This is the logarithmic format of that inverse. I'm going to write, why am I writing too small there? So here's the second, and both of these, number 1 and number 2, this is still the inverse of the original question of this top y is equal to 5 to the x. It's just in another format. These two, number 1 and 2, are both the same function. So any exponential function can be rewritten as a logarithmic function, and we're doing that for the inverse equation here, not from the original up here. That's where this question will lead to confusion. So let's do it again over here. So we're going to wipe out the function notation of the original. So this is the original function. Now I'm going to do the inverse function by switching. Okay, so we're going to switch that x and y. So here's x equals 1/2 to the y. Already, this is now my exponential function. My answer for that first little part. And now for the logarithmic version. Okay, so my logarithmic version is going to look like, I'm going to write down the log. The value on its own, the answer, is going to become the argument. So that's going to become the big value next to the log. On the bottom, that subscript hanging off of the G, that's going to be the base of my original exponential format. So I'm going to put the base was 1/2. And over here, I'm going to put my y value. The exponent is going to be over here. Okay, so then that is my logarithmic form of that inverse. Okay, and we're going to continue to use that pattern for switching your exponential into your logarithmic forms throughout the rest of the lesson. That's all that there really is today. Okay, so let's do it again. Rearrange the logarithmic functions into exponential form. So now we're going from logarithmic to exponential format. Okay, so like what that means is that this 6, I'm going to start with that number that's in the subscript position. It's kind of like at the bottom of my equation. That's going to be my base. So it's going to be 6 to the exponent of the answer is equal to the argument. Okay, right, that's the argument here. The argument's by itself. So here's the x value. I'm starting with that bottom number here, that 2.5, that subscript is my bottom number. It's going to become the base. It's going to be 2.5 to the y is equal to the argument, the answer. We don't have to solve those. There's 2 unknowns there. So we're just grabbing logarithmic format and putting it into the exponential form. The next ones, we can, like, there's nothing to solve for the next ones, but we can write it in exponential format using that pattern, and just we'll double check that it makes sense. So 2 is that bottom number, that subscript. So that's going to become the base. That means 2 to the exponent is going to be that answer. So that means 2 to the 6 equals 64. Right? The argument becomes the answer. So 25 is my base. The argument becomes the answer, AA. And so this is 25 to the half equals a 5. So for both of these, there's no unknown, but we can double check using our calculators or just our general knowledge. Is 2 to the 6, 64? Is 25 to the half 5? Yes and yes. So now we've got the logarithm with a base of 8. The logarithm of 1 with a base of 8 is equal to 0. That's how we could say that out loud in words. So that 8 becomes, because it's at the bottom here, that's going to become my base. My argument is just the answer on the other side. And this 0 is my exponent. So 8 to the 0 equals 1. That's also correct. This little bottom number is my base. I'm going to say that the argument, this 1/9, is the answer. And the exponent is, sorry, I should say the answer is my exponent. So this whole thing is to the 2. And that also makes sense. 1 squared is 1, 3 squared is 9. So we're just double checking at the end that we've used the patterns correctly to change the logarithmic style into the exponential style. Example 6, now we're saying evaluate. So like, what is this stuff equal to, right? Okay, so that subscript is the base, that argument is the answer, and we don't know what this value is. So I'm going to use y's up here. So 6 to the y equals 36. So you can use a bit of guess and check there, or your logic. It's 6 squared is equal to 36. So y in this case is equal to 2. Okay, so it's a bit of guess and check there. So this is, the bottom number here is 9, so that becomes my base. That argument becomes the answer on the other side. And so we don't know what this is, y. So 9 to what exponent gives me 3? So we have to think about how if we had a fraction up top here, that would mean the square root of 9 because of the index of 2. So the square root of 9 is 3. So y is indeed equal to a half here. And then this last one, the base of 10 to what exponent equals 10,000? Okay, so 10 to the 4 would give me 10,000. So y is equal to 4. Okay, so that's how we do it. These are the big ideas of today's lessons. Not too bad. Find the value of x for each example. Okay, this is the same thing over again than the previous. Oh, sometimes we're looking for what the base is. So we're looking at this format, this logarithmic format. I'm going to write out the base to the exponent of x is equal to 27. So we need this fraction to flip. So that would mean that this exponent would have had to have been a negative exponent. So when we have a negative exponent, it flips. So in my mind, I'm thinking, okay, now that I put that negative in that position of the exponent, it's flipped to 3. Right, so 1 over, I'm just going to put it as an aside here. If this is negative, that's going to turn into 3 over 1, but I need it still to turn into 27, so it's got to be not squared, but to the power of the exponent of 3. Okay, so, oops, that becomes positive now that I've already flipped it. So it's to the exponent of negative 3. That's going to give me 27. So x is equal to negative 3 here. Or for this next logarithmic one, it's the bottom number here is my base. My subscript becomes my base here. And I'm saying 5 to the 3 is equal to the argument, right? So this argument is always the answer. 3 then becomes my exponent. So before I was looking for my exponent, now I'm looking for the argument or the answer. So this is just that x is equal to 5 times 5 times 5 is 125. So this one in exponential format is x to the 2. This argument becomes the answer on the other side. Okay. So x squared is equal to 1 over 16. So if I'm trying to get x by itself, I got to square root both sides. And so that releases just x by itself, and I'm going to say the answer here is positive or negative 1/4. Okay, so the tricky part of this question is that your unknown, we're switching what the unknown that you're solving for is. It's not constantly that you're looking for the exponent or that you're just trying to evaluate the logarithm. It's switching in all 4 of these. Oh, and I'm just going to leave you guys with this part D just for a second. One moment, please. You guys try that. And you can even try the next example as well, and then we'll take it up in 5 minutes. Hi guys. Okay, so let's see how you did. So this one, we should have written 3 on the bottom. The bottom becomes the base. To the answer here is equal to x. 3 to the 0 is equal to x, so x is equal to 1. So the argument becomes the answer on the other side, and then 0 is our exponent. It takes some time to get used to it. So write the following in logarithmic form. Okay, so if we want this to be in logarithmic form, the base becomes that little subscript, and the answer over here becomes the argument. And so that would mean that the exponent is on the outside over there. Or logarithm of a base of 4. And we're going to have this answer become our argument. And that's going to be equal to 5. Or this logarithm of a base of 2 is going to have the argument of 128, and that's going to be equal to 7. Or this logarithm of the base of 1/3 is going to have an argument of 27, and that's going to be equal to x. Okay. So scientific calculators can perform logarithmic operations using the log button. So look for that on your calculator. This button represents logarithms in base 10 or log 10. Okay. So if we are asked to find a logarithm like these questions here, in our calculators, we can just use our calculators and type in, for my calculator, I have to type in 1000. And I want to make sure that my calculator is back in degrees here, and then I'm going to click log. So when I do that, I get the answer of 3. Or like when there's nothing written next to the log here and there's no unknown there, that's assumed to be 10 here. So this would be 50 and then the log button, and that would give me 1.7 approximately. And then this is the logarithm of a negative 1000. Well, I can take the logarithm of 1000, but I can't take the logarithm of that negative number. So if we put that into our calculators with the negative, you're going to get an error message. So this does not exist because 10 to the exponent of y is never going to be equal to negative 10,000. Okay, so the homework for this section is 1C on page 451 of your textbooks, and we'll take a little 15-minute breather. There's also these extra practice questions that you can jump into right now if you'd like, because this will kind of like solidify once you go through these 9 questions. That'll just kind of make it sink in where that the subscript goes into the base position, that the and where the other 2 values go. Okay, so and the answers are just down here, so you can check yourself right away to see if you're doing it right or wrong. Okay, so do that now. We will come back at I'll give you like 15 minutes to do these 9 questions of extra practice, and then check yourself, and then we'll do 15 minutes of break. So we'll come back at 10 o'clock to then do the second lesson of today.